Hello, worksheet 4. We went over a lot of this in class, but little reminders. How do meter voltage measurements compare with oscilloscope waveforms? Your meter measures what value of voltage. Your oscilloscopes show what value of voltage. How do you check to see if a relay coil is good? Same way you check an inductor to see if it's good. I think that's enough of a hint. Measure the resistance of the motor windings. And then what check can be made by a multimeter on all used motor windings prior to install or reinstall. It's a good habit to get into. What is the inductive reactance of a 13 millihenry inductor at 2450 hertz and 3300 hertz? Well, I just happen to have my spreadsheet open. I've got my conversion spreadsheet open. So 13 millihenry is 0.013 henries. So inductive reactance XL is 2 pi. So equals 2 times pi. In a spreadsheet, it's pi open close parentheses times frequency, and I'm going to reference the frequency here in the E2 category above, times E2. Okay, it's going to be a 0, but when I put in 20 hertz, I don't have the formula corrected. 2 pi times frequency times inductance. So I got to get in my inductance, 0.013. That's my inductance. Okay, it's a 0. So I'm going to put in 20 hertz. There's the first answer. And that unit will be in ohms. So if you need it, you type it out so you remember. Then it says, what's it going to do at 4500 hertz? Well, let's find out. Okay. And then what's it going to do at 33,000 hertz? And I'm not going to do that one. At what frequency would the inductive reactance be equal to 0? And you sort of saw that. If you put in a 0, you get an inductive, for frequency, you get an inductive reactance equal to. And then at what frequency would the inductive reactance be large or infinitely large? Well, what you saw is as the frequency increased, the inductive reactance increased. So if you could put infinity in up here, you would get an infinity answer out. So from a practical standpoint, very, very large frequencies, meg, gig, gigahertz, that range, your inductors become extremely reactive and opposed to it. Now it says, given a circuit with a 56 millihenry inductor and a 3K resistor, what frequency will the reactance of the inductor equal the resistance of the resistor? This is a special frequency known as a corner frequency. Well, I know I want to come up with 3K or 3000. And I can copy this formula down. Copy, which is Control C, Control V. It's going to reference my frequency there. So, what about 15? Way too small. What about 3600? We're getting there. What about 40,000? Oh, I went over. So somewhere between 3600 and 4000 is, you'll get an answer. There is a frequency such that the inductive reactance of the inductor equals the resistance given. And this is a special frequency known as the corner frequency. I can also just set the equations together. I can set, since I know I'm wanting 3000, that's my inductive reactance. That will equal 2 pi times an unknown frequency times my inductance value, which I gave you. Whoops. I didn't change my inductance value. So that wasn't 56. This is 56. So you see now I'm way too high. Details, details, details. Got to keep track of the details. So my formula is X of L is 2 times pi times frequency times L. And why did it do that? My mouse likes to jump around if I touch the keypad. Equals 3,000. What I don't know in this equation is I'm given L, it's 0.056 or 56 millihenries. 2 and pi are a constant, so to find that frequency I'm going to take the 3,000 and divide by 2 times pi times 0.056. And I can come up with a frequency directly versus up here I was using trial and error. Much faster. Square root of -1, don't look for a special symbol. It's just I or J. I'm just trying to jog your memory. What inductance value at 60 Hertz would give a reactance of 500 ohms? So now I'm using this equation and I'm saying you know the frequency, you know the reactance you want, you don't know the L. So again, we're just manipulating this equation to come up with a number. It's just algebra, one variable. What are the voltage drops across the resistor inductor in series in a series resistor inductor circuit in which the inductive reactance equals the resistance and both are 645 with 5 volts applied? This is an Ohm's law problem. We know the voltage, what we need is the impedance. And we need the impedance in terms of magnitude and angle. Well, what we know is our resistance is 645, so that would be a real part. And we know our imaginary part is 645. So our impedance works out to be 912 at an angle of 45. So if I take 5, angle 0, because voltage has a reference angle of 0, and divide by 912, angle 45, I will get the current flow. It's just Ohm's law. We're just now using complex numbers. Analyze using software the currents and voltage drops in a series resistor and inductor circuit in which the inductive reactance equals the resistance and both are 645 and with 5 volts applied. Okay? So I want to know the currents and the voltage drops. I want to find the voltage drops. Well, we've got to go back into Spice for that, right? So I think I left it open. It's off the screen. You can't see what I'm doing. There's Spice back. So, new schematic. Do I have my frequency for that? Want to minimize, not close. Oh. Maximize. I'm clicking the wrong thing here. There we go. 645, 645. So I've got to come up with an inductive reactance at 645. So the inductive reactance we typically use is 10 millihenries. So 10 millihenries is what I've got. That's one I've got. I need it to be 645. So I know what I'm shooting for. I know my inductance. I don't know my frequency. So if I take 645 and I divide by 2 times pi times the value of my inductance, 0.010, I should get it. So here's my frequency for number 11. Or number 12. So number 12, and this is another reason I like using spreadsheets. So I can put notes in here. Number 12 space frequency. Okay, so that would be equal to 645 divided by 2 times pi times my inductor, 0.010. That's what we have in the lab. That's 10 millihenries. And, oh, it all got in there, didn't it? Control X. And Control V. So I need a frequency of about 10,265.5 hertz. Okay, so 10,265.5 hertz. I need that for the analysis, and I can modify based on components. If I'd had a different inductor, used a different inductor, you'd wind up with a different frequency. That's what that means. So now I go to Spice, give myself a new circuit. Actually, I've got 2 circuits open. I want a voltage source. It says everything is in series, right? So I'm going to rotate my resistor. Do my inductor. I'm going to put in a ground. Gonna connect dots. Has this gotten old yet? Have you gained skill? That's what you're after. Yeah, you can do this once and you can know how to do it, but you won't be good at it until you do it 10 times or so. Okay. My inductor is 10 milli. My resistor is 645. And my voltage source, I think, was 5. That's what I recall. So I got to go into the advanced mode, and I'm going to do the 5. I'm going to do it here. So that takes care of that. For my analysis, I'm going to do AC analysis. I'm going to do linear 1-point sweep. 10265.5. 10265.5. Now when you're setting up this frequency, don't try for that frequency. Just get somewhere near when you actually build the circuit. So, okay, there that is. Now simulate and run. And maybe it'll look alright up here. I'll just cover up the AC analysis line. Okay, frequency. My voltage is 5. My angle is 5.00 times 10 to the minus 15th degrees. Now, sometimes when Spice does a calculation, you get a really, really small number, but you call it 0. And this one you could call 45. So I have a voltage here of 45, 3.53. I have a voltage here 5, angle 0. And what did the worksheet ask for? Analyze the software. The currents and voltage drops in a series resistor inductive 645. Okay, so I need the currents, which are all the same, a little over 5 milliamps, about 5.5 milliamps, because it's a series circuit. And the current angle does change a little bit, but if you were to read it, it would read the same everywhere with a multimeter. My voltage drop across my inductor is 3.53 at an angle of 45. What I don't know is the voltage drop across my resistor. And one of the things I want you to discover is it should be about the same as the other one. this 3.53. So if I go back to my Excel spreadsheet and get it here where I can see it, use it, convert it. I think I can slide it there. Let's see, okay, I've got the whole thing done. Slide that way. There we go. So these are polar rectangular. So I've got a 5 angle 0, and I've got a 3.53 at an angle of 45. So here are my rectangular imaginary numbers that represent these two values. Okay. So I'm going to subtract from the 5, 0 this other one. So 5 minus 2.5 is 2.5. And 0 minus 2.5 is minus 2.5. So just like I did in the last video, I wound up with 2.5 and minus 2.5. Which tells me that my voltage drop across the resistor is equal to 3.54. My voltage drop across my inductor is 3.54. So they're both the same. And at this special frequency that we talked about, where they're the same, you will wind up with equal voltage drops across there. 1314 says build and measure the voltage drops in the series circuit. 5 volts applied. Well, you know that you get 3.5 across both. You know you've got 5 there, and you know the current. So I just want you to measure the voltage drops. If your function generator is set up for 5 volts, what would the peak to peak on the oscilloscope be? That's just a simple conversion. Using a 10 millihenry inductor with an internal resistance of 24 ohms and a series inductance of 620, at what frequency is required to make XL equal to R? That's essentially what we did. In the real world, inductors have internal resistance. We ignored it in our first calculation, but I did take that 24 and I added it to the 620. So I had 645 ohms. That's where 645 came from. And that is what we calculated for the frequency in number 12. Where'd the spreadsheet go? There's that frequency, the number 12 frequency. And that is the frequency where my 645, or my inductance, is 645, and my resistance of the whole circuit would be 645. Counting the internal of the inductor. What is the current in a parallel resistor inductor circuit in which the inductive reactance equals the resistance, and both are 645? Okay, so now I want to do the same thing again, except these have to be in parallel. So basically I can just change my circuit around. I got to close the analysis if I'm going to modify the circuit. That's why it clicked at me. I'm going to put in another resistor. I'm going to cut that resistor out. I'm going to connect dots once I get my scissors off. Escape. And I got to make this resistor 645. My AC analysis will be the same frequency. I don't change anything. Just the configuration of the circuit. Simulate and run. Now this interestingly gives me 1 voltage, which is 5. So I've got 5 volts across everything because everything's now in parallel. My currents wind up being a little different. My inductive current and my resistive current are about the same, about 7.8 milliamps. But what you see is there's a phase angle difference. I've got a negative 90 on the inductor, and I've got one of these 5e to the minus 15th, or essentially a 0 on the resistor for phase angle. So these currents are actually out of phase, and that my source is having to supply 10.9 milliamps at a phase of 135 degrees. Now I want you to measure the voltages and the currents. So you would measure the currents with a meter, so you don't have to worry about these phase angles. Okay. One thing I do want to show you though, which is interesting, is what if I take these polars, because it's parallel, right? Can't move that. Okay, I can probably do it this way. There we go. So we got the magnitudes of the currents. So I've got 0.7. I'm going to do everything in milliamps. So 7.75. 7.75 angle minus 90. Minus 90. So this is my real and imaginary components. And then I go down to my resistor, 7.75 at an angle of 0. So this becomes my resistor current. So this line is my inductor current, this line is my resistor current. And then my total current would just be the sum of these two, because my source has to supply the current that winds up going into both. So if I was to add 7.75, 0 plus 7.75 and minus 7.75 and 0, I wind up with 7.75 and minus 7.75. And did I do that right? Minus 90. Yeah. So I'm just adding them. 7.75 minus 7.75. And I get a minus 45 degree angle. This is telling me I've got a phase angle of 135. So that's 90 plus 35. So that puts me in the second quadrant. This did not convert right. So my real goes positive, my imaginary, that's fourth quadrant. This should be fourth quadrant. Okay. So I like my answer better. Minus 45 and 135 is, oh, I know why. Because SPICE does negative current, so the positive current would be at 135. And if you're conventional, the angle would then change 180 degrees. So I get the same answer. I get 10.96. So you can see that in AC circuits, my inductance, my inductive current and my resistive current add up to my source current. Even though the phase angles make it look, if I just look at it in terms of magnitude and phase, looks like that's just not possible. But indeed, Kirchhoff's current law is still preserved. Okay, what else is on there? Based on the calculated current for the parallel resistor inductor, how much power would the resistor 620 have to dissipate? I'm going to take the current through the resistor in terms of magnitude. I'm going to square the magnitude. I'm not going to worry about the phase angle. And then I'm going to multiply it times the value of resistance. And then that would give me the power. Or I could take this voltage, which I know is 5 volts, and I could take the current through my resistor and get the value for the power as well. I do have to respect phase there, though. Yeah, it's better to do I squared R always. Always. And then what VARs will the inductor have to do? Well, in a power circuit, power is I squared R. For VARs, it's going to wind up being I squared, whatever the current through the inductor is, I squared, times the value of the inductive reactance, which we know to be 645. So we should get the right answers that way. And is the parallel circuit safe to build on the bench using a 1/4 watt? So once you do the power calculation, you'll know if it's safe to build. Where's the spreadsheet again? Let's just do that. So what is 5 times, if I do the current, I get what? I got to put an equal sign. You always got to start with an equal if you want to do a calculation. 5 times 0.00775. So it gives me that much wattage. If I do the I squared R, I'm going to square the 0.00775 and multiply it times 645. Should get about the same answer. 0.00775 quantity squared. And you notice I get the same number. So my watts for this is about 40 milliwatts, which makes it safe to build. That answers 20. And for my VARs, I'm going to get the same thing. I'm going to get exactly the same number of VARs. So I got identical VARs, and I'll have identical power. And what you notice in terms of my inductive reactance and my resistance being the same, you could predict that up front. And that's where we're heading in this class, just so you know. Anyway, there's your video to look at, to contemplate. And thanks for watching.